The video demonstrates extracting geometric data from simulations, using logical conditions to control positioning, and saving information to a file. Variables are employed to manage dimensions and simulate motion. Logical conditions help maintain dimension positions, handle collisions between objects, and to show messages. Messages can be stored in a file for analysis, aiding in complex simulations. In this video, we will show how to extract geometric information from a parametric construction or a motion simulation and use of logical conditions to issue messages and save this information. In the previous video, we showed how to do a simple simulation. Let's create a variable r and set it to 40. See that we can change the hand crank circle directly by editing the dimension, and also clicking twice on the circle entity. The radius of the circle is now the variable r. Let's create the connecting rod angle and the horizontal center line. Simulate. See that the dimension oscillates in and out. Depending on the angle of the connecting rod, the fixed positioning point of the dimension indicated on the screen is inside or outside the two straight lines for calculating the angle. How can we force the angular dimension to always stay inside the two lines? The solution is to position the dimension between the two straight lines regardless of the connecting rod rotation angle. To resolve this, use a logical condition to check the value of this angle and position the angular dimension according to this angle. Creating an ang1 variable. Associate the ang1 variable with the center line of the connecting rod. The angle value is calculated from the endpoint to the starting point or center of an imaginary circle, indicating the center and endpoint. Test parametric processing. See the list of variables ang1 is 0. Reprocess parametrically. Now, ang stores the connecting rod angle. With a logical condition test whether the connecting rod angle is less than or greater than 180. Create a new variable ang2 which, depending on the value of ang1, create the logical condition. If variable ang1 less than 180. Assign ang2 to 179.25. Else assign ang2 to 180.25. Finish logical condition. Construct a straight line from quadrant 0 of the circle with angle with variable ang2, and position it outside the circle. Since the radius of the circle is r, we can define the length as 2 times r plus 8. Delete the dimension and create a new dimension with its positioning at the end of the straight line with angle ang2. Simulating movement. Let's activate the process parameterization option so that the logical conditions are processed and also variable values are calculated according to the geometric conditions during the simulation. Now the dimension is being positioned inside. Reposition the circle dimension. Remember that we indicated a variable for the circle. We can also view this variable in the dimension. How do I associate this angle with a variable? Create a new ang3 variable. Associate ang3 equal 180 minus ang1. And reposition into the logical condition if ang1 less than 180. It is associate ang3 equal ang1 minus 180. And reposition into the logical condition if ang1 greater than 180. It is moved to the else condition. Note that now ang3 is calculated correctly regardless of the connecting rod position. How do I show the value of this angular dimension as text in the screen? Creating the text. To show the content or value of a variable, define a text with that variable prefixed by a hash and enclosed in parentheses. Angle equals ang3 hash in parentheses. Now the value of ang3 is shown graphically. But still, there is a small adjustment in the positioning of the angular dimension. When ang3 is close to 180, the dimension is yet positioned outside the straight lines. This happens because the value of 179.25 that we used should be closer to 180. Let's edit it to a value of 179.75. Now is correct. Let's edit the simulation commands so that the process parameterization and show variable list options are always active. This way we don't need to activate these options every time the simulation is tested. In 3D, there are functions to check whether bodies and faces collide. How can we do a 2D crash test? Let's check the collision between the connecting rod and the piston guide. Create a new dist variable. Calculate the distance between the piston guide and the connecting rod. Create a vertical line. Associate dist with a distance on the y-axis. Indicate starting point and final point on the y-axis. Check the current value. Create the dimension between these 2 points. When does a collision occur? The dist value is calculated from the end point minus the start point. When dist is less than 0.001 or negative, there is a collision. Creating a logical condition. If dist is less than 0.001, show the message plus the dist variable value. There is no collision. Let's edit the simulation so that a collision occurs. Click on the piston dimension with the Control key pressed and edit the piston offset to 20. Message indicated with a collision. If there is a collision, abort the movement the first time it occurs. Let's insert a brake command inside the last if block. Simulation aborted. In a complex motion simulation, there are dozens of messages. The message commands can be saved in a file. It is not necessary for the Show Messages option to be active in the dialog box. Let's save the messages to an external file named Simimins. First, delete the brake command so that all messages are output. We can also show the angle message when collisions occurs. Simulate. Open the file. See that the messages created in the message commands have been saved. This way, all information collected during a simple or complex simulation can be saved for future analysis.